My name is Bryan. I'm gonna be going over this course for the next like 8 weeks or so. So yeah, that's my name. And if you ever have any questions, you can always just ask in the chat, private message me. That's fine. Um, so yeah, I think we can start now. All right, so everyone can see the screen. Yes. All right. Well, basically, I think the way that these classes are going to go is that I'm going to be like giving out the lecture notes about a week in advance, or maybe a few days in advance or so. You can look over them. You don't have to, but if you ever want to like look at what we're going to be doing during class, you can see it's posted on the classroom stream. And yeah, so during class, I'm going to be basically reviewing the notes which pertain to topics that I think are important to understand, and there will be questions or example problems at the end, which we'll do together. And yeah, that's basically it. So with that out of the way, I think we can start. Oh, and by the way, there will not be any like assigned homework or anything for this course. All right, so week one, I chose circles as a topic because in the AMC and many other math competitions, you'll always see geometry problems that involve circles in some way because, well, they're just such a easy shape to work with. So first off, I think you guys all should be familiar with the area and circumference, which is pi r squared and 2 pi r respectively. And so the first part that I want to go over is how to find the area of a sector. And a sector is basically just a section of a circle starting from the center. You draw 2 radii out in to any 2 points on the circle, and then the area of like the slice that it forms is the sector. And you'd basically find this area by taking the degree measure that the arc makes up, and then taking that, dividing by 360, and multiplying by the area of the circle. So it's very intuitive, kind of like how, like, if the degree measure is 60 degrees, then that means that it's 60 over 360, or 1/6 of the area of the circle, meaning that the area of the circle would be, or the area of the sector would be 1/6 area of the entire circle. All right. If there are any questions throughout the meeting, you guys can ask. I'm just going to reiterate that because everyone is here to learn. So asking questions is the best way to learn. Anyway, next up is the Two Tangent Theorem. And basically, this just says that for any point and a circle, for one, there are 2 tangent lines from that point to the circle. And the tangent line is a line that intersects the circle exactly once. And as you can see in the diagram, that the point is A, there's a circle, and it's tangent at points B and C. Basically, this theorem states that AB equals to AC. And this is very useful. And you can show this because if you draw the line from the center of the circle to like to tangency points, even though it's perpendicular, that's the property of a tangent line. Then we connect the center to the point A. And here we have 2 congruent triangles. And this basically works because of symmetry. So yeah, AB equals to AC. And this will be more useful for things later on. And next, this one's also kind of, I guess, intuitive. It's just that if you connect the line between two centers of two tangent circles, which are again circles that only intersect each other at one point, then this line between the radii, as you can see in the diagram, is perpendicular to like that line that passes through this point. And basically that means that this line here is tangent to both circles at the same time. All right. Are there any questions so far? Or if not, we can kind of move on. All right. Here we can go into the more advanced kind of parts of the circle, or basically find an area of a segment. And basically a circular segment is defined as like this kind of weird compressed semicircle shape that's shaded in blue. And basically, and basically that's just found by taking the area of the sector that is formed when you take the two endpoints of your segment and connect it to the center. You take the area of the sector and subtract the area of that triangle to find this shaded area, like so. And this is very useful for AMC problems because a lot of them have these irregular shaded areas, like so. So,
which one is the circular segment?
Can you repeat that?
Which one is the circular segment?
The circular segment is the part shaded in blue.
Okay, thank you.
No problem. And the sector is the part, is the entire thing. So like, you can think of a sector as like a pizza slice, and a segment as like, I don't know, only like the curved part of the pizza slice with that horizontal edge. So we can do an example of this. For example, if we take a very commonly seen sector is one of 60 degrees. So if you have like a 60-degree sector, I hope everyone can kind of like understand my diagram. And we take this segment. And how would we find the area of the segment if this radius is 1? Well, first you would find the area of the sector. So you have 60 over 360 times pi times 1 squared. And this was from here earlier. And this is just, sorry, 360. This is just 1 over 6 pi, right? And then we subtract the area of the triangle. And the area of an equilateral triangle with side length s is s squared times the square root of 3 over 4. I'm assuming that this is a formula you guys are familiar with as well. Anyway, if not, you can ask and I'll go more in depth into that. But basically, once you do that, like, you know, side length is just the radius of a circle. So this is 1, and area of the triangle is root 3 over 4, which means the area of this shaded segment is pi 1 over 6 pi minus the square root of 3 over 4, like that. So that would be kind of how this circular segment works. And this works for any angle, although usually the angles have to be kind of nice enough so that you know how to find area of a triangle like that. But yeah, the concept still remains. All right. All right, so next we have inscribed angle theorem, and this is very cool actually. And you can see in the diagram, basically for any arc And we define an arc as just like, you can think of a section of a circle or a curved like line segment between 2 points on a circle. The angle formed by the center of the circle when you connect a line segment to the two endpoints of that arc, like in a sector, this angle in the center is equal to the angle of the arc. Okay, that's how we define an arc. Next, when we take these same two endpoints of the arc and choose any other point on the circle that is not on the arc, just on the other side of the arc, such as this point right here, or this point right here, the angle is going to be half of this center angle. All right. Is that, does that make sense, or?
Yes.
All right. I don't think it's too important to know how to prove this. I can't think of how to do this off the top of my head. Just know that this fact exists for whenever you're solving problems, because it does come up a lot. All right. And on a similar note, if we take a tangent line to a circle and it's tangent at some point, and then we choose another arbitrary point here, such that we form an angle theta here, then again, any angle from these 2 points to a different point on the circle, they're going to be equal to this angle right here, like this angle right here. And this is only for a tangent line. And again, so this is a little bit more obscure, but it's still good to know. And anyway, all of these notes are already available. So if you ever need to refresh it, that's fine. All right. And lastly, not lastly, but next we want to talk about circles and triangles. And basically the two special circles every triangle has, and they're called the circumcircle and the incircle. So the circumcircle of a triangle is the unique circle such that each vertex of the triangle lies on that circle, like so. And basically, if we take the center of the circle, usually called O, that means that the distance from O to A, B, and C are all equal. And that's going to be the circumradius of the triangle. And that's how the circumradius is defined. It's the radius of the circumcircle. So basically, the area, not the area, we can actually find this circumradius, usually denoted with a capital R, is equal to A times B times C over 4 times the area. And A, B, C each refer to a side length of the triangle. So like if this side is length A, this side is length B, this is length C, then these would be the values of A, B, and C respectively. Additionally, this capital A refers to the area of the triangle itself, and yeah, 4 times the area. Again, this isn't like very easy to prove right now, at least. So just again, know that this formula exists whenever you need to find the circumradius. And I do want to note that this is usually combined with Heron's formula for the area of a triangle, which we will go over in the coming weeks. So just a side note. But anyway, let's move on to the next circle, which is the incircle. And like its name, it's a circle that is inside a triangle. And it's such that each side of the triangle is tangent to the circle. And there is only one unique circle for every triangle that satisfies these properties. And the cool thing about the in radius, which is the radius of this circle, is that it's equal to 2 times the area over the perimeter. And this is actually pretty easy to show because when we draw like the radii to the tangency points, they're perpendicular. And then if we connect to this incenter is denoted I. I'm not going to write that, but if we connect it to the 3 vertices A, B, and C, you'll see that we form 3 triangles that with the incenter B and C, incenter CA, incenter AB. And the area of each of these triangles is like the radius times the side length divided by 2, right? Because base times height over 2 is area of a triangle. And what that means is that we have the in radius times AB plus BC plus AC all over 2 is going to be equal to the area of the triangle. So then if we rearrange that and the perimeter is just AB plus BC plus AC, we get this 2 times the area over the perimeter is equal to in radius. And yeah. So does everyone follow this?
Yes.
And there is also a special case for this kind of in radius, and it's for a right triangle. Okay, so for a right triangle, the in radius, let's draw it. It has this cool property that, for one, it forms a square right here because you have a right angle and this is a right angle. So these are parallel, and this top part of radius, and you have this top part and this bottom part are also parallel, and everything's right angle. And then you also know that this is R and this is R, which means that this is a square. And what's cool about this is that we don't need to use this 2 times area over perimeter formula. There's an easier way to do this for a right triangle. And that takes advantage of the two tangent theorem that I mentioned earlier. And if we let the side lengths of the triangle be A, B, and C, for example, for the right triangle, we'll see that, or I claim that R is just equal to A plus B minus C over 2. And the reason why this works is from the two tangent theorem using, well, the 3 vertices of the triangle and the incircle, we see that this length equals this length. This length is the same as this. And we also have R and R here, right? So when we add A and B, we're adding basically 2R plus, we'll call this one, I don't know, just these 2 tallies. And then this length here is the 3 tally one. And C is just the 2 tally one plus the 3 tally one. So that just cancels this part out, and you're left with 2R as the numerator. So you divide by 2 and get R. All right, that's kind of a neat trick. Okay, so if that's good. I'll move on to the, I think probably the most advanced part of this, which is called power of a point. This is also usually the most useful in more difficult problems. So basically, this is using. Oh, sorry, let me rephrase that. The power of a point basically takes a circle and a point and gives some kind of relation between certain line segments that can be formed using that circle and the point. So the first case is when the point is within the circle. And this is just the first diagram right here. So it's just saying that for any point inside the circle and for any two line segments or chords within the circle, AC and BD, their only condition is they intersect at this point. Then you have AE times EC equals to DE times EB. So you have AE, EC, DE, ED. So you can think of as just the two sides of a segment that are split. The product is always going to be the same. And the reason why this is true is because of similar triangles, or it is similar triangles. So basically, from vertical angles, you have angle DEC is equal to angle AEB. And then again, from the, I think it was called, I forgot what it's called, inscribed, okay. The inscribed angle theorem, you have the angle ABD equals to angle ACD. These two angles are equal. And this is because they both face the same arc AD. So they both face this arc, these two angles are the same from that theorem. And that means that these two triangles are similar because their angles are all the same. And basically what similarity means is that corresponding parts of these triangles must be in proportion. So that means that we can just rearrange proportion to get a statement. You have, for example, AE corresponds to DE from each triangle, and you also have BE corresponds to CE. And obviously, when you cross multiply, you just get exactly this. So this is the reason why this works for any circle, any point, any line segments drawn at any angle. So yeah. So the next two parts of PowerPoint both revolve around the point being outside the circle, and they're both kind of interconnected. So this one states that if we have a point B and a line AB that's tangent to the circle, and meaning that A is only intersection point, then AB squared equals to BC times BD. And the reason why this works is because of similar triangles. So if we connect AC and AD, we claim that this triangle ABC is similar to the triangle DBA. And the reason why this works is because, for one, angle B is shared by both triangles, meaning that it's going to be the same in both triangles. And this angle right here is equal to this angle right here because of that, because of, well, this right diagram here, this exact theorem. So there's like kind of a direct application there. So then again, we have two similar triangles, and then you can just set up a proportion where you have this AB from the smaller triangle corresponds to BD the big triangle, and you also have BC of the smaller triangle corresponds to AB of the bigger triangle. So then again, you'll find that it's just exactly the formula. And lastly, this is kind of a corollary of the second one, and that's just if we have a point C and a circle, and you draw any two just lines that intersect the circles, as you can see in the diagram, and they don't have to be tangent or anything, then you have CB or BC times AC equals to CD times CE. And with this one, you can use similar triangles to show this as well, but the easiest way to see this is, or I think the coolest way to see this is by just drawing a tangent line. And you can just apply the second equation, you could say, to CF and CA and CE. And basically each of these quantities just going to be equal to CF squared. And since they're equal to the same thing, they themselves have to be equal as well. So yeah, and this is okay because from the second circle, we can see that the angle at which this line BD intersects at the circle is not relevant to the accuracy of the statement. So that means that for any like any chord, not chord, but like any line from C to the circle, this is going to work for these segments as well. All right. And we'll see an example of this later in the problems. Okay. Okay. I think that is the last of the what I call the lecture, or just concepts, I could say. So I like to end it off usually with some of my common tips and tricks when it comes to circles. And the number one most important is you always connect the centers of the circles to important points in the diagram. This usually refers to tangency points, or I don't know, vertices of shapes, stuff like that. And as you do more problems, you should be able to identify what points are important. And again, the Pythagorean theorem, which I actually haven't mentioned, is very, very common in these types of problems, and we'll see that later as well. So a lot of times you can try to find right angles. Points of tangencies are usually the best bet when it comes to that. And this goes for any kind of problem in general, but don't be afraid to use variables. They're kind of inevitable, so you have to be able to work with them. When you're doing types of like area problems, be creative. A lot of times there are ways to partition areas that make it easier. We'll see that as well. And also, you don't have to have a great diagram. As long as it's serviceable, it should be fine, especially since you do have time constraints. And the last thing I do want to emphasize is symmetry. Circles are inherently very symmetric, and you can take advantage of this in a lot of ways in problems. And mainly it's just if everything is kind of like the same under the same conditions, like it has to be, well, symmetric. And we'll see examples of this as well. So those are kind of all my key points. So I think we move on to the problems. And if you'll notice, some of these problems are going to be starred. I mentioned it, and those are the ones I kind of think are important. So, like if you are reviewing the notes after class, which would not be a bad idea, just try to understand how to solve the problems that do have stars on them. All right. And speaking of which, I think we can start the problems. I kind of want to skip this problem. I don't think it's useful. Okay, let's move on to the next one. This 2004 10B number 16 that we see in the top left. Three circles of radius 1 are externally tangent to each other and internally tangent to a larger circle. So what is the radius of the larger circle? All right. So the first thing to do is draw a diagram. And this one is going to be kind of like, well, well, this is not going to look that great, but it works. So we can kind of assume that this is a good circle, and these are three identical circles of radius 1. And this is just one big circle of tangent to everything. So I'm going to give everyone maybe like a minute just to think, and we can kind of discuss how you would approach this kind of problem. So yeah, you have some time to think about what steps we should take. All right. So I'm asking this just to everyone. And if you want to answer the question, you can type it in chat. So when we see this kind of problem, what is the first thing that you should do? It's kind of, I mentioned this in my tricks, tips and stuff right over here. What should we do to make this easier to solve or possible to solve? And yeah, please type in the chat, or you can say it out loud too. That's fine. Okay, Ian, that is a good answer. Draw the centers to each other. And yes, you should be connecting the centers because we need straight lines to be able to work with, because you can't really do anything just by staring at these circles. But this itself is not actually enough. We also need to connect the center of these circles to the points of tangency. And I'm only going to do this one on the bottom right because, well, it's symmetric, so it's going to be the same for the other circles as well. And we're not done yet. We still need to figure out the distance from this center, the center of the circle, to here. And now the idea behind exploiting symmetry here is that we know each circle is the same, radius 1. So that means that the center of this circle is going to be like the center of this triangle formed by the three circles. And this is because if it wasn't, then this diagram would not be symmetric, which doesn't make sense because there's no indication from the parts of the problem that it would not be symmetric. So this means that we can kind of connect this circle or the center to the center of this smaller circle. And I did forget to mention this, but another cool thing to know is that for any two circles, be it externally or internally tangent, you have their tangency point, and the two centers are going to be collinear, meaning that this line between the two centers of the circles is actually going to be the same line as between each center to the tangency point, like so. And again, the reason why this can be seen as true is because if it wasn't the case, then somehow the line between centers have to be either above or below. But there's no way to tell whether it would be above or below because it would be asymmetric, and circles are very symmetric by nature. So that itself is kind of good reasoning for why this is the case. So now all that we need to do is add up these line segments. So we're given that this is just 1, so you need to find this. And now when you have you've broken down a bigger problem into a smaller problem, what you can do is kind of just only focus on what's necessary. And that's just this triangle here. And since this equilateral triangle, we can find this length in many ways. I'm just going to leave this open to everyone. What is this length? Just if you have your answer, you can type it in the chat. Well, okay. The answer is, well, one of the answers in the chat is correct. Actually, is it? I take that back. None of them are correct. Actually, no. I'm overthinking this. Actually, Mason and Leo X12 are correct. This length is 2√3/3. And I think we can find this, for one, by noting properties of the centroid. And this is going to be, or this line is going to be 2/3 of the height. And I think that's actually kind of, we'll do a different way. How about we use the Pythagorean theorem here, or properties of a right triangle, 30, 60, 90 right triangle to be exact. For basically any 30, 60, 90 right triangle, which means the angles of 30, 60, and 90, the size is going to be in the ratios of 1 to root 3 to 2. And the reason why this is because each 30, 60, 90 triangle is just half of a right triangle. And so if we, not right triangle, equilateral triangle. If we take an equilateral triangle and just drop the altitude in the middle, you'll be split into two 30, 60, 90 right triangles. And if this equilateral triangle has sine length 2, then each of these bottom parts would be 1. And then use the Pythagorean theorem, get this to square root of 3. And then because of similar triangles, this ratio is preserved no matter the side length. So we can kind of use that for what we have here. We know that the side length of the equilateral triangle is going to be 2. And that's because it's just each radius is 1, so it's 1 plus 1. And that means that this side length here is 1. This angle is 30, which means this 1 corresponds to the square root of 3 side. So that means that the ratio of the hypotenuse to this side length is 2 over square root of 3. That means that 2 over square root of 3 times 1 is going to be the length of this hypotenuse, which is just 2 root 3 over 3. So our final answer would just be 1 plus 2 root 3 over 3, or 3 plus 2 root 3 over 3. All right, are there any questions about this? Okay, so does everyone understand? I'm assuming everyone does. And if you don't, you can, oh yeah, I also do want to mention that above each problem, I have these labels that say like 2000 something, 10B or 10A number, whatever. And these are just the AMC tests that I pulled these problems from. So if you ever don't remember how we did in class, or you're just curious, you can go on AOPS and look up, just look up AMC 10 for that year and find that problem. You can find solutions from other people for these problems as well. So if you ever don't know how to do a problem, you can always just look up its answer. And it'll also have like the method of how to solve the problem as well. All right. So I think I want to do, all right. So let's do this problem. 2003 10A number 17. Number of inches in the perimeter of an equilateral triangle equals the number of square inches in the area of its circumscribed circle. What is the radius in inches of the circle? So first thing I want to mention is this is actually an algebra problem, just kind of hiding underneath the shell of a geometry problem. And that's kind of because you don't need a diagram for this. All you need to know is the formulas for, well, perimeter and area of its circumscribed circle, right? So this can actually be quite tricky because you have to be super careful when you're kind of doing this. So I think the most reasonable variable to have is going to be the side length of a triangle. And we can let it equal to s. All right. So number of inches in its perimeter is just going to be 3 times s. We want to equal the number of square inches in the area of its circumscribed circle. So to do that, we need to find the radius of the circumcircle. And interestingly enough, this length that we found in this problem here is actually exactly the circumradius of the equilateral triangle. And I'm sure you guys can calculate this at home as well. If you, for example, if this length is s over 2, then this is just going to be s root 3 over 3. Yeah, so you can verify this at home, but this radius length is going to be s^3/3. And basically, when we square it and times pi, because that's area, we can kind of just do that and solve. So we have 3s equals to 1/3 s squared pi, which means that s equals to 9/pi. So is this our answer? Yes or no? Is this the answer to the problem? 9/pi. That's right, it's not. And this is because the problem asked to find the radius of the circle, and we clearly defined s to be the side length of the triangle. Right. So again, this is just another tip. The problems are meant to trick you, so you really have to read them carefully and make sure you give them what they ask for. So the radius is s times the √3/3, as we see here. So then you just multiply it. I'll put that in. You just multiply by the square root 3/3, and you get 3√3/3/pi. And that is the answer. All right. Okay, let's move on to the next start problem, because this one's interesting. We have 3 semicircles of radius 1. You can kind of see that they're overlapping with each other. If you have, you can just draw the other 2 where they would be. We have 3 semicircles of radius 1 and 1 of radius 2. And centers of the small semicircles divide AB into, well, these 4 line segments where you have 1, 1, 1, 1. Basically, it just says that they're all equal. And you need to find the area of the shaded region. And this is something I did touch upon earlier, and with problems that involve these irregular areas, you have to kind of be creative and find, there are multiple correct interpretations or whatever. Just find a working diagram, or not diagram, just extra lines that will make it so that well, the area is calculatable, basically. So right off the bat, we can see that the shaded area does not have any like specific formula that you can use. So we have to kind of try to break up these semicircles into areas that we do know how to find. And I think I'll just do this. I think the most logical thing to do would be to take these intersection points and connect them to this center like so. Does that make sense? Oh, okay. Right, and I do want to point out this is not the only way you can do this, but this is just one way you can do it. And now you can, it's actually easier if we draw more lines. And now what we can do is we split this into shapes that we do know how to calculate. For example, we have this leftmost section here. This is equal to 1/3 of a circle because this equilateral triangle is 60 degrees. And you can see this is equilateral because this side length is 1 and this side length is also 1. And well, it's kind of symmetric. And oh, actually, I shouldn't say that. And we also know that this side length is 1 because it's the radius of this left semicircle. And basically each of these segments is a radius of one of the semicircles, so they're all equal, so it's equilateral. That means the degree measures are all 60. So this measures 120 and the same with this one. So this must mean that each of them is 1/3 of a circle. And this applies to, well, both of the ones on the end. And now with that taken care of, we're left with two equilateral triangles and a 60-degree sector. So the area of, well, this part is just going to be 1/3 pi because it's 1/3 of a circle with radius 1. And it's the same with this part, it's also 1/3 pi. Each of these equilateral triangles have side length 1, which means that the areas are going to be √3/4 times 1², which is just, well, √3/4. And of course, we have this 60-degree sector, which I actually kind of used as an example earlier. And from that example, we found that this is pi/6. Actually, this is just pi/6 because we don't have to subtract the equilateral triangle. All we have to do is add the sector, which is just going to be 1/6 of the circle. So then now all we have to do is add these all up to find area of the unshaded region. And we can see that there is no overlap between any of these sections. So there isn't anything that we could have miscounted or anything like that. So, well, if we add, this is 2/3 plus 1/6, that's 5/6 plus √3/2. And now this is the unshaded area. So we can find the area of the shaded region by simply subtracting this from the area of the entire semicircle. And the entire semicircle has radius 2, and it's half a circle. So it would be 4 pi divided by 2 is 2 pi, would be the area of the entire semicircle. So then if we take 2 pi minus this whole thing, and we can just get, that's just 7/6 pi minus √3/2 as the answer. All right. Does anyone have any questions on this problem? And again, if you do have any trouble with these problems later, you can always, again, look them up on AOPS as well. But I do like answering questions. So yes, that is the link to the problem. And I do recommend, for one, trying to do all these problems before you look at the answers, because, well, you don't get as much benefit out of already knowing how a problem is done than trying to work on it with just what you know and just your own ideas, basically. All right, so that I do want to move on to this problem because this one is actually surprisingly simple. And this is a perfect example of using Pythagorean theorem, and we'll see that later, or not later. But if you see the problem, it says it's a square ABCD with side length 2 and has a semicircle on AB, and we have this tangent line CE to that semicircle, and we ask the length of CE. And basically, the key insight to this problem is that it's CB is tangent to the semicircle at B, and that can be kind of seen from the construction with the semicircle, and that C to this point F, or the point of tangency, is equal to CB from the two tangent theorem. We know that it's a square, so every side is 2, and this CF must be length 2 as well, because it's equal to CB. And again, we also have EF and EA are also must be the same because of the two tangent theorem, where EA is tangent to this semicircle, so is EF. So if we let this line equal X, EA is also equal to X, right? And now you have dE equals to 2 minus x because the sine of a square is 2. So you have to add up to 2. And now this is just the Pythagorean theorem on triangle CDE with angle D being the right angle since it's a square. So you have 2 squared plus 2 minus x squared equals to 2 plus x squared. All right, so this is kind of one kind of way you can see how a Pythagorean theorem can come up in these problems involving circles. So after that, this is just kind of simple algebra where you have 4 plus 4 minus 4x plus x squared equals x squared plus 4x plus 4, and x squares just cancel out, and you have 1 4 cancel with this 4, and eventually you're left with 8x equals to 4 and x equals to 1/2. That means that CE is just 2 plus x, which is just 5 over 2. And that would be the final answer. So yeah, does everyone follow this? All right. Oh, I left my notes up here. Okay, well, that's fine. Okay, well, we are kind of, well, okay, well, I'll skip this problem for now and come back to it at the end. So this one I've already kind of solved. So I mean, you can look at it if you want, but it's whatever. This problem is just a perfect example of power of a point. You can read it. It says in triangle ABC, we have AB is 86, AC is 97 in a circle. Center A and radius AB intersects BC at points B and X, and BX and CX have integer lengths. So basically, the key word here is integer. And when you see integer, it usually means that there's some, well, very restrictive, it's a very restrictive kind of bound, you could say. So the key thing to note is that we can extend CA to the other side of the circle. For example, this is point D, and the radius is 86. So we just add 86 to this line. And since we know the length of AC, we also know the length from C to the circle is 11 because it's 97 minus 86. So from here, we can use power of a point on point C, where 11 times 183, this is 11 plus 86 plus 86, that's equal to CX times BC. And we know that CX and BC must both be integers because BX and CX have integer lengths. So this means that we can factor this product, and well, it's just 3 times 11 times 61 is equal to CX times BC. And now triangle inequality can be used to show that CX right here, for example, if we draw this length is 86, the diagram isn't great, but you'll see that CX has to be greater than 11. And if it's not, that means that AXC would not be a real triangle. This means the only possibility is CX is 33 and BC is 61. So then the final answer would be BC is equal to 61. So yeah, power of a point. All right, and I think we'll go over like a few minutes, if that's okay. This is going to be the last problem that we're going to be doing, which is this one. It's very similar to the first question, but you'll see that circle A has radius 1 and passes through the center of the circle, while B and C are of unknown radius, and they don't pass through the center of the circle. And basically, the key point here is that the radius of circle D is 2 because its radius is the diameter of circle A, right? So that means we know the radius is 2, so we can look to find another way to kind of express this radius and using the radius of circle C or circle B while in it. So if we take the centers of the circles, as that is kind of the easiest way to consolidate a diagram, we'll see that it looks something like this, right? So now we can use the Pythagorean theorem to kind of, well, find this radius in a different way. So if you let the length of this be r, the radius is r, which is unknown. We know that this side length of this triangle is 1 plus r, and same with this. And the side length is 2r, which means that if we drop the perpendicular from the center of the circle to the side length, it's just going to be r. And you can see that because it's just the radius of the circle. So now we can use the Pythagorean theorem kind of twice to solve this problem. First off, you have to find this entire height, which is the square root of, well, r plus 1 squared minus r squared from the Pythagorean theorem. Then you subtract 1, and you get this part right here. And now you add this, and I mean, this length refers to this blue part right here. And now we need to find this hypotenuse, and that's equal to this thing squared plus r squared. We take the square root of that, and we know that this entire expression is going to be equal to 2 minus r, because this is just the expression for the radius. The radius is 2, and when you subtract r, you just get this hypotenuse. And we're kind of running low on time here, so I won't be able to finish this problem, but just know that the method of just looking for right triangles to find unknown side lengths is going to be very useful. So if you do want to finish this problem by yourself at home, you can. You can just check your answers as well. So yeah, that's that. And lastly, I do want to touch upon this, where basically I have, well, not that. Each problem set is going to have basically what I call this challenge problem, which is, it's like a problem that I think is more relatively difficult compared to the other problems. And it's always going to be pertaining to that topic. And this one is going to be 2019 AMC 10B number 20. And here it is. Again, you can also find this, you can just find this in your lecture notes. But it's just for if you want to see if you're completely, or not completely, but like if you are in good shape to do very well, you can kind of try these problems by yourself, and you can also check your own work from the problem citation that I gave. So yeah, that I just want to say that is an option for everyone to do. I may or may not post a video about how to do the problem. I'm not completely sure yet, but yeah, that would be it for this class. So yeah,
Thank you.
No problem. If you guys have no questions, you guys can just leave.